Let's greet Fereshteh for coming here and present the seminar. Thank you. And to talk about her research. And okay, you can go.
Thank you for giving me this opportunity. Okay, my presentation today is on multivariate Hasse-Schmidt derivations, which are generalization of univariate Hasse-Schmidt derivation on exterior algebras that was introduced by Letterio Gatto. And these Hasse-Schmidt derivations have very nice features and applications in different areas of mathematics, such as like in geometry, for example, they can describe completely the sugar calculus on Grassmann varieties. So I think they are very nice to study. So just as an outline, I would start with the definition of Hasse-Schmidt derivations and some properties, and then I move to multivariate case, and there is a theorem which is a kind of generalization of Cayley-Hamilton theorem, which is proved by the new definition of trace operators. And then there is one example which I just tell the example. I hope you will understand. To start, just for convince, we will consider this notation throughout the presentation. V is a vector space over a field in K with this basis, and this wedge is the exterior algebra, which the zeroth power is K itself, and these products are generators of the jth power of the exterior algebra of V, and this is just the formal power series with values in the exterior algebra. Now the Hasse-Schmidt derivation on the exterior algebra is just an algebra homomorphism like this, which can be presented by a formal power series, which the coefficients of are in the morphisms of the exterior algebra. The name derivation comes from the fact that this equality is equivalent to something like a Leibniz rule identity, which is, if we expand this identity, what we get for each I is this. I will explain some properties very shortly. If the Hasse-Schmidt derivation is invertible, then the inverse also is a Hasse-Schmidt derivation. And in case, we know that in case E0, the scalar part is invertible, then the Hasse-Schmidt derivation is invertible, and we denote the inverse by d bar. And the coefficients are here in the morphisms of the exterior algebra. The nice proposition is that if F is an endomorphism on the vector space, and if we define this power series, then there exists a unique Hasse-Schmidt derivation, which if we restrict the derivation to the V itself, we get the same series. Now, if this df is invertible, we call the inverse the trace operator polynomial. I will explain the reason of the name trace here just in a moment. And before, just notice that because these two are inverse of each other, then the d bar f on v is exactly obtained by this 1 minus fz. Now, if EIs are the eigenvalues of the components of the inverse, we call the eigenvalues the traces of f. The reason is that, the motivation of the name trace is that can be that if we consider V to be vector space Cn with this basis, then we can write the matrix of F to be like this. And then if we compute d1 of F, apply d1 of F, d bar 1 of F to this vector, what we get is exactly the trace of the matrix of F. And also, if we computed the d bar n, what we get is the determinant of this matrix. Now there is a theorem which is can be like the generalization of the Cayley-Hamilton theorem, which says that if we have an endomorphism here and B be the corresponding Hasse-Schmidt derivation, then this identity holds, which the EIs are the eigenvalues of the components of d bar i's in the inverse. Now I would move to the multivariate case. Just again for just convince, I would like to introduce some notation. This underline, by this underline I mean like n tuple of everything. Like here, the underline means n tuple of variables, and this is underline I is n tuple of integers, and just this absolute of underline I mean the length of A, the sum of all the components. So the n multivariate Hasse-Schmidt derivation is again an algebra homomorphism. Just in this case, we increase the number of variables in the powers in the algebra of power series. And again, in this case, we can represent the derivation by some power series, which the coefficients are the endomorphisms of exterior algebra. And the set of all n multivariate Hasse-Schmidt derivation we denote by HSN. We can define a multiplication on this set by considering if these two are two Hasse-Schmidt derivations, then we define this product to be the sum of these compositions, and then the multiplication of these two Hasse-Schmidt derivations is defined by this equality. This multiplication makes the set a multiplicative monoid. Now we have again the lemma, which says the similar Leibniz rule for multivariate derivations again, in that these two are equivalent as we had before in univariate case. Now, for example, if we have the canonical basis for Zn, then in this power series, the coefficients of Z k is just DEK, which one is the indicate position. And these DEKs are usual derivation of the exterior algebra. And now this proposition is like the similar proposition as before, that if we have an endomorphism and the formal power series, then there is a unique multivariate Hasse-Schmidt derivation such that if we restrict the derivation on the vector space, we get the same series. And also, if the multivariate Hasse-Schmidt derivation is invertible, then the inverse is also a Hasse-Schmidt derivation. The next proposition, which we call it integration by parts, this is a very important proposition. These two formula, which are called integration by parts formula, they actually hold for univariate Hasse-Schmidt derivation and multivariate case as too, and we use this formula to prove the theorem, the main theorem for for multivariate case.
I have a question on notation.
Yes.
On that slide and other slides. When you write Fy, Zy, what's meant here? It's a product of, don't know.
These Fi's are just an endomorphism. Like this one is for each I, Fi is an endomorphism.
Mm-hmm. And this product is really the product on Vz, on the power.
Yes. This is in the. This is like a power series, just this variable.
Yeah. So is there? This is like finite in some sense, or can it go to infinite?
No, it can be infinite.
Okay.
I mean, yes, it can be finite, but can be infinite as well.
Okay.
There is no restriction.
Okay, thank you.
No. Okay, so from now we consider underline V to be a tuple of endomorphism of V, and then we consider a unique Hasse-Schmidt derivation V bar such that if we restrict V bar on V, we get this. Like here in the proposition, our F is like this, just a finite number of sums. And then we have that if U is indicate power of the exterior algebra, this D bar ZU is just a polynomial with the coefficients in wedge V. This is not like a power series. Here, D bar Z is finite. And as a consequence, if the length of our indice is greater than J, then this Jth power of V is in the kernel of D bar I, which means this is equal to 0. And now we define the I trace of this n-tuple of the endomorphism to be a scalar satisfying this equation, just like the eigenvalues of this operator D bar I's. Now I'm going to somehow prove the theorem, but with an example, I will show what do I want to prove, and then we reach the theorem. just let V be a two-dimensional vector space, and we have a pair of endomorphisms of V, and D bar is a unique Hasse-Schmidt derivation with this condition that the restriction of V is this, and D be the inverse of the D bar. Then if we apply D bar on the U of any, like if U and V be any vectors in V which their wedge is not 0, if we apply this on U wedge V, then what we get by the definition of this D bar, we get this, and if we substitute the values, we get this. And by extending this line, we have like power series that, like, this one is a coefficient of Z1, this one is a coefficient of Z2, and so on. And like here, we have this one is a coefficient of Z1, Z2. Now, in the integration by parts formula, which is this, in the expansion of this formula, we want to compute the coefficients of Z1, Z2 here. In this formula, in the right-hand side, what we get is just this, like the only coefficient of Z1, Z2 here is just this, which is 0 by the proposition that we had before. And in the left side, if we expand the left side, what we get it is this. Now, by the definition, these D bars are our traces. So just replace this D bar by the traces. And since trace is an scalar, we can write something like this. And since V is arbitrary, this part, this parenthesis here, is equal to 0. Now, because these two are inverse of each other, a simple computation shows that, like, the 1, 0 is phi 1, the 0, 1 is phi 2, and the 1, 1 is these two compositions. So the previous, this last equality becomes like this. Now, if we consider the matrices of these endomorphisms and denote them by A1, A2 in any basis, like A1 is this matrix, A2 is this matrix, then we can compute the trace of phi 1, phi 2 as like the determinant of this matrix. And this matrix is like phi 1 U, phi 2 V is like the matrix is a matrix whose the first column is the first column of A1, and the second column is the second column of A2, and for this, it's similar for this matrix. And D10 then is just the trace of A1, since here, like D10, we have nothing here, so this is identity. So here, like, we have the determinant of AB 0, 1, and here we have the determinant of 1, 0, BB, and the sum of the determinants is just the trace of A1. And the similar for the tau 0, 1 is the trace of A2. So the equation that we had before by these traces becomes this. Now, if we consider phi 1 is equal to phi 2 with the same matrix like A, then this equality that we had before becomes just this, which is the usual classical Cayley-Hamilton theorem, and it shows in which sense we are saying that these theorems are like generalization of the Cayley-Hamilton theorem. Now, by considering like the coefficients in the similar way, like by considering the coefficients like z1, z2, z3, that the product of the variables, we get this theorem, which says that if we have these endomorphisms and D bar are the unique Hasse-Schmidt derivations correspond to this obtained from these endomorphisms as before, then this identity holds for these traits. And if we look at this one, if we have just one endomorphism, this is just this theorem, what we had here. The theorem is somehow the generalization of this one in the univariate case. Now one can see that the definition of these traces, these are like the special traces. I mean, the indices here are like if we have an n-tuple of indice, every component is 1 or 0. We don't have, because if we want to consider like the components to be greater than 1, then everything is, this is not, this would not be false, but it's a bit more complicated. We cannot have the equation like this. This equation will be a bit more complicated. Now these traces, if we look, can be obtained by this equality, as we have seen in the case of two-dimensional, like we had that here. We had that like here, tau 1, 1 is just the determinant of these two matrices. And in general case, this is also true that these trace can be obtained by the determinant of such a matrix. So this formula motivates us to make this part, to name this part. So we introduce a notation that if A is an n-tuple of n times n matrices, then this is just the determinant of this matrix. Like here we have, this matrix is just like the, in a matrix whose A1 column is the A1 column and of A1 and so on. And the other ones are just the columns of identity matrix. For example, here, if we have a triple ABC, then these are the different i's that can be considered. For example, here, like D1, 0, 0, we have a matrix whose the first column is the first column of A, and second and third columns are those of the identity matrix. Like here we have a matrix whose the first column is the first column of A, second column is the second column of B, and third column is the third column of C. Now, what we like as an application, what we can see is that if we can define this trilinear form, A star B star C to be this form using these DIs. Then theorem says that this form is totally it's Q-symmetric, which means if we get the sum over all the permutations of A and B and C, what we get is 0. The reason is that if, as I told before, these are just the components of this sum. I mean, if we get the sum over, if we get the sum with the sign, with the proper sign over these indices, what we get is just our traces. So these, so if we compute all the permutations and consider the signs, what we get is just the traces. And the theorem says that this is totally skew-symmetric. We can also consider the other coefficients in the, sorry. Yes, in what we have here, or I mean in general, not just in two cases. In general, we can consider the coefficients of all the monomials or the polynomials that we have here and get the same result for them. And so in case that you are interested in the Hasse-Schmidt derivations, I highly recommend this book and the other papers as well, but this book is quite complete and nice, and thanks for listening to my presentation.
Okay, thank you, Fereshteh. Let's all quick talk. Let's all please. Thanks, Fereshteh, for great talk. Yes. Thank you. Any questions? Okay, so I really like the talk. It was really digestible, let's say, for a new result. I will just